In this lecture session, I am going to demonstrate the topic on single-phase full-wave control rectifier with RL load. There are two types of circuits normally we consider. Number one, that is M2 connection, and number two, that is B2 connection. So let me discuss the configuration. In case of M2 connection, normally we are using a center tap transformer whose the primary winding is connected to the supply directly, and the secondary winding, it is center tapped, in which we are adding the load, that is RL, and we are using two thyristors, that is T1 and T2. In case of B2 connection or bridge connection, we are using the fourth thyristor, which is actually connected in a particular manner which will form the bridge, and we are using the load across the bridge like this manner, and we are using a AC supply over here. So that means in case of M2 connection, when we apply the AC supply, then the current starts flowing to the primary winding, and for the mutual inducting effect, then the voltage is set up across the secondary part. As it is center tapped, that is why we consider the number of winding of the upper part and the number of winding in the lower part, both are same. That is why the voltage will appear across the upper part and the lower part, both will be same. That is defined by suppose Vs and Vs also. And two thyristors are there, and this is load. And we are operating with RL load, that is why RL load is connected, and which is directly connected to the middle half of the secondary winding. In this case, when during positive half cycle, what happened? So in case of the primary winding, the upper part will be positive and the lower part will be negative, as well as the same thing can be happen for the secondary winding also. So at is center tap, that is why the voltage appears across the upper part. This one will be positive and this one will be negative, that is defined by Vs. Same amount of voltage can be appeared across the lower half also, and the potential and the polarity will be same, that is this one is positive and this one is negative. Okay, when this will be positive and this will be negative, that means we can say the first thyristor, I am talking about this one, that is VT1, that should be in forward biasing condition. Whereas when in case of the lower half, when this one is positive and this one is negative, that means we can say in this particular case the lower SCR, or that is T2, that is in reverse biasing condition. That means we cannot fire this thyristor at this situation. Suppose we are applying the gate pulse across the first thyristor, then what happened? Then the thyristor will be turned on. Once the once the SCR becomes on, then the current starts flowing to this direction, which is defined by this arrow. That means current is flowing from right hand side to left hand side across the load for positive half of the supply voltage. Once the supply voltage starts to the negative half cycle, that means after pi, when the supply voltage goes to negative, then what happened? Then the polarity of the supply will be changed. Then it will be positive and the upper part will be negative. And a similar effect can be happen in case of the secondary winding also. So it will be positive and this will be negative for the upper half, and for the lower half it will be positive and it will be negative. Once it will be positive, then current try to flow from this direction. That means we can say then the thyristor T1, that should be in reverse biasing condition, which was in the first case in forward biasing condition. And in this case, for the lower thyristor, that is T2, will be in forward biasing condition. Then we should apply the triggering pulse across the gate of the thyristor T2. Once the thyristor becomes on, then automatically the current starts flowing to the load in this direction, which is defined by this arrow. That means both the cases I am talking about the two cycle, for positive half cycle and for negative half cycle. So during positive half cycle, thyristor T1 is in forward biasing condition. It can be on by using proper gate pulse. Then the thyristor T2 is reverse biasing condition. And for negative half cycle, that can be found that then the thyristor T2 will be in forward biasing condition. Then we can apply the gate pulse across the gate terminal to turn on this thyristor. At the same time, the upper thyristor that will be in off state as it is in reverse biasing condition. So this is actually happen for the positive half and the negative half for the supply voltage. Okay, but in the both cases, it has been noticed that the voltage appear across the load that is same, because when thyristor T1 was conducted during positive half cycle, then the polarity of the that is VO, that is load voltage, it will be positive and it will be negative. That means, and the current is flowing from right hand side to left hand side. Similarly, when thyristor T2 will be fired for negative half cycle, then again the polarity of the load voltage, it will be positive and it will be negative, and the current starts flowing from this direction. That means if we consider the both current direction, that will be remaining in the same direction, means across the load, that is right hand side to left hand side. That is why we can say by using two transistors, both the half, means I am talking about the both half for the supply voltage, that will be converted in the one direction, that means in the forward direction. That is called actually rectification operation. So this can be happen, or this is actually the working principle in case of M2 connection or center tap transformer connection. Whereas in case of B2 connection, normally the both switches will be conducted at any instant. Suppose T1 should be fired at the same time T2 should be fired, as well as if T1 try to fire, T4 should be fired at the same instant. Suppose considered at the first case, when the supply voltage goes positive and current IS starts flowing, and we are applying the triggering pulse across T1 as well as T2, then the current starts flowing in this direction to T1, then load, then T2, and coming back to the supply. Okay, so this can be happen in case of the positive half cycle. After crossing pi, when the supply voltage goes negative and when the negative cycle starts, then what happen? Then automatically T1 and T2 will be in reverse biasing condition, so it will be commutated automatically. Then we should, at the same time, T3 and T4 both will be in forward biasing condition. That is why we should apply the triggering pulse, proper triggering pulse across the thyristor T1 as well as the thyristor T2, but it will be in same duration, same instant. Once the thyristor T3 and T4 will be switched on, then the supply voltage, then the current from supply voltage starts flowing in this direction, as it is happen in case of the second negative half. That is why the supply voltage goes negative, that means it will be positive and it will be negative. That is why current starts flowing from supply to this direction to thyristor T3 to the load and coming back to the supply through thyristor T4 in this way. So this is the direction of the current. So similarly, just like a M2 connection, we can say, but the both case for positive half cycle and negative half cycle, the current direction remaining same. That is, when T1 and T2 was conducted, then the current direction was from upward direction to downward direction across the load. Similarly, for the negative half cycle, when T3 and T4 starts conducting, then the currents should flow from up to downward direction across the load. That is why the direction of the current remaining same for this particular purpose. As well as in case of voltage, when T1 and T3 was conducted, then the voltage, polarity of the load voltage, it was positive and it was negative. And when T3 and T4 starts conducting, at the same way, the polarity of the load voltage, the upper part will be positive and the lower part will be negative. That is why we can say, by proper conduction of the T1, T2 and the other T3, T4 for the consecutive cycles, means positive half cycle and negative half cycle, both the cases, the current and voltage direction same in case of load. That is why we can say the positive half and the negative half both will be converted in terms of voltage and current that to the same direction or in positive direction. That is why we can say this is a rectifier operation. So actually both circuits, the operation principle is almost same, but in the first case we have conducted 2 thyristors, in the second case we have conducted 4 thyristors. So the whole operation of the M2 connection that can be reflected on the waveform also. Here we have taken a few parameters from the M2 connection circuit, that is Vs, that is actually supply voltage, that is Ig1, that is the gate current across the thyristor T1, Ig2, gate current across the thyristor T2, V0 is the output voltage across the load, I0 that is output current that is through the load, and VT1 that is actually the terminal voltage across the first thyristor T1, and VT2 that is the terminal voltage across the thyristor T2. In this particular operation, first thing that is very important to understand, that is when the one thyristor starts conducting, how much voltage will be appeared then the second thyristor when the thyristor was in off state. Okay, that is true for any circumstances or for under any situation. If one switch starts conducting, then the other switch should be in reverse biasing condition and the switch was in off state. That is why it is evident that if one switch starts conducting, then the switch is working as a short circuit. That is why no voltage will be appear across that particular switch. But then the total voltage and how much voltage will be appeared across the second switch. Okay, let me discuss the whole thing by using KVL. Okay, see, if we apply KVL across this particular loop, this whole particular loop, that means it have started from this voltage for forward biasing condition. That means Vs should be equal to voltage across this switch, that is VT1, minus voltage across this switch, that is minus V2 minus VT2. Why we have taken minus term? As the direction of this position, the position of this thyristor is opposite. That is why when the thyristor T1 is in forward biasing condition, then the thyristor T2 is in reverse biasing condition. That is why and Vs that should be equal to VT1 minus VT2 and minus that is this position, that is Vs. So we can write the expression VAN, it should be equal to VT1 minus VT2 plus VBN. Okay, so we can rewrite the expression, that is VT2 equal to minus VAN plus VBN plus VT1. Why we are going to calculate the term that is VT2? As we know, in the positive half cycle, then VT1 is triggered, but then VT2 was in off state. That is why our approach is to find out how much voltage will be appeared across VT2 when the switch was in off state, or we are going to find out the blocking voltage across VT2. Okay, that is why we have changed the expression in this way. Now, after simplification, we can have that is VT2 equal to minus Vm sin omega t plus 0. Why? Because during positive half cycle, the voltage appear across VAN, that is equal to Vm sin omega t, and the lower part, that is again Vm sin omega t. As it is a center tap transformer, that is why voltage appear to the upper part and lower part, both will be same. That is why we have written the expression in this way, that is VT2 that should be equal to minus Vm sin omega t minus Vm sin omega t, this minus term due to presence of this one, and this minus term as it is the reverse bias. So as it is the lower voltage stands for, that is VNB, as we are defined by VBN, that is why the expression can be defined by minus Vm sin omega t. And Vt, as it is in conducting state, that is why it is behaving like a short circuit. No voltage will appear across the first switch. That is why it stands for 0. So ultimately, we can have the expression that is Vt2 equal to minus 2 Vm sin omega t. Okay. So this is the final expression that is actually which define the blocking voltage across the thyristor T2 during off state. Okay, that means this blocking voltage can be maximum at the point when omega t reaches 90 degree. Okay, that is why we can replace the equation that is Vt2 equal to minus 2 Vm is a very important expression which is actually called the peak reverse voltage or peak inverse voltage at the point of 90 degree, where the maximum supply voltage where the voltage will be maximum in case of supply voltage. So that is defined by the peak inverse voltage Vt2 equal to minus 2 Vm. Okay. So when the thyristor T1 conducts, then T2 received the peak reverse voltage and the value is minus 2 Vm. Okay. One more thing, as it is operating with a RL load, that is why it should cover two quadrant operation. Actually this thing had described in my previous section in case of the half wave rectifier with RL operation. As the load is, as the L load is there or inductive load is there, that is why during positive half cycle of the supply voltage, the inductor gets energy from the supply, is stored energy inside it, and the stored voltage across the inductor that will achieve up to the maximum point, that is supply voltage Vm. When the inductor voltage is fully charged, then it starts discharging. So during charging of the inductor, the supply voltage and the inductor current both are positive. That is why it will cover the first quadrant operation. Then the energy or the power that will be transmitted from supply to load. Once the inductor starts discharging, then as the charging and discharging both currents remaining in the same direction, that as well as we have applied a negative cycle across the supply, that means voltage will be negative, but still the inductor discharging current that will be remaining the same position. That is why it can be treated as positive current. That is why the multiplication of the negative voltage and the positive current that will give you negative power. So that is defined by the fourth quadrant operation. So in this operation, we can say then the total power that should be delivered from load to supply, means the power is feedback from load to supply. That is why during RL operation, always any rectifier that can cover the two mode operation and which will be taken from the first mode operation, or that is the first quadrant operation as well as the fourth quadrant operation. Now the waveforms. So the total working principle can again be described to the proper waveforms also. Okay. Here the first thing, that is supply voltage, as we have given AC supply and AC supply, that is why this is a waveform of AC supply. Okay. And we have applied the triggering pulse across the first thyristor for the positive half cycle. That is why Ig1, that is alpha, this is the triggering angle that is given in the positive half cycle only. This one, again, the next positive half cycle, next will be given at the point of 2 pi plus alpha. Okay. Similarly, the next getting pulse, that is Ig2, that should be given across the second SCR, that is T2, and the pulse should be given at the negative cycle of the supply. That is why Ig2, that is alpha, that is applied at the point of pi plus alpha here, and next will be given on the 2 pi plus alpha, 3 pi plus alpha. That means Ig1 all stands for the positive half cycles of the supply, and Ig2 for the negative half cycle of the cycle. Okay. Now see, if we extended the part in this way, when Ig1 is given and when the switch or thyristor T1 becomes on, then the current starts flowing in this direction. That means the supply voltage immediately will appear across the load. That is why the supply voltage is appeared across the load. That is from alpha to pi. At this position, the inductor starts storing energy, okay, to a maximum value, that is Vs, and just cross the particular part, that is pi. When the supply voltage goes negative, then the inductor tries to discharge. And charging and discharging current both are in the same direction. That is why, yet for due to presence of the negative half of the supply, the thyristor can be in negative biasing condition, but still due to presence of the stored energy across the inductor try to discharge in the same direction with respect to previous one. That is why still the diode that is why the SCR still under in working state. So it can be worked up to the particular point where the inductor will be discharged fully. That is why it continues its conduction up to the point, suppose pi to alpha, where the next triggering pulse is given across the second thyristor for negative half cycle of the supply. That is why for alpha to pi, that is the waveform that should be followed from the supply voltage, and after pi, when the inductor try to discharge at a particular point, and the inductor starts discharging and it will reach a particular point, suppose at that point we are applying the next triggering pulse to the thyristor 2. That is why again, if the thyristor 2 starts conducting, as we have given the negative half cycle, then it will be positive and current starts flowing in this direction. That means immediately the voltage which had constant in magnitude with respect to Vs, that should be followed by the load voltage. That is why again the load voltage that will reflected from this negative half of the supply voltage. That means positive half and negative half both will be in the same direction. That is why we can say it's a rectifier operation. But due to presence of this inductor, always there is the extension part is given over here due to discharging path. Okay, so it is the voltage waveform from the output voltage across the load. So in the same way, we can deliver what will be the current waveform across the load. This is a current waveform. As we know, in case of the first switch was operated, then the inductor starts storing energy inside it. That means the inductor current is gradually increases. So on the other way, we can say then the circuit current is gradually increased. That is why from this conduction position from alpha to pi, due to presence of inductor, the current is gradually increases from its lower value I0 to a particular value, suppose capital IO1. Okay, and when the inductor starts discharging at this region, where at this duration, that is pi to pi plus alpha, the inductor gets discharged. That is why the inductor current is gradually decreases from its higher value to a initial lower value, that is I0. In a similar way, when the thyristor T2 starts conducting, again the inductor starts storing energy, and the inductor and the circuit current starts increasing from its initial I0 value to a value in the particular value, and again start discharging. In this way, it will be repeated from the next cycle onward. Now the important part, that is terminal voltage across the SCR or blocking voltage across the SCR when the SCR remaining off state. It is true when the switch T1 or the thyristor T1 starts conducting, then T2 stops working. When the T2 starts conducting, then the thyristor T1 stops working. That means when T1 starts working, no voltage appeared across thyristor T1 as it is behaving like a short circuit. Then the total peak inverse voltage that I have calculated before, that is 2 Vm minus 2 Vm total voltage appeared across thyristor T2. Similarly, from the the negative half cycle of the supply voltage, when T2 starts conducting, the total peak inverse voltage, that is minus 2 Vm, that will be appeared across T1, the first thyristor. The same phenomena can be reflected on the waveform also. See, in this particular region, I am talking the point that is suppose alpha 2 pi plus alpha, in which the capacitor was charged and discharged and the switch T1 was in on state. In this duration, we can say T1 was in on state. That means across T1 or terminal voltage across T1, there is no voltage is there, that is a zero voltage. Okay, as it is behaving like a short circuit. When this thyristor turned off for the negative half of the supply voltage as well as the thyristor T2 turned on, then what happened? So the voltage appear across T2, that should be 0, and total peak inverse voltage will be appear across the first thyristor. That is why when the first thyristor was on, then the voltage appear across the second thyristor, that is peak inverse voltage, that is minus 2 Vm to this point. So from alpha to pi plus alpha, there is no voltage across T1, total peak inverse voltage is appear across T2. Similarly, suppose from alpha plus pi to 2 pi plus alpha, in this region, as T1 stops conducting, then the total peak inverse voltage is appeared across T1. Then as the T2 starts conducting, as it is behaving like a short circuit, that is why no voltage is appeared across the thyristor T2. So in this way, it will be repeated from the next cycle onward. So this is all about for the waveforms in case of the output voltage and output current as well as the terminal voltage across the two thyristor T1 and T2 respectively. Same thing can be done by using B2 connection also. But the waveforms will be similar, almost same. That is why the one change can be done for the gate pulse. As in case of the B2 connection, there is a four thyristors. That is why we should apply the gate pulse G1, G2, and in this case G3, G4. Or sorry, IG1, IG2, and in this case IG3, IG4. Similarly, the terminal voltage, that this axis can be replaced by VT1, VT2, and it can be replaced by VT3, VT4. So there is a small difference by using these two circuit, M2 connection and B2 connection, and apart from this notification, the other operation and the wave shape of the output voltage current and input voltage current almost similar to each other. Now we are going to calculate the average RMS value as well as the inductive load is there. That is why going to analyze the steady state operation as well as transient operation. First, we are going to calculate or we are going to define the expression for average value. Okay, so VDC, that is stands for the average output voltage across the load, that should be equal to 2 by 2 pi, that means number of peaks 2 divided by 2 pi, integration of alpha to pi plus alpha, means any peak that is confined between a particular duration that is defined by this limit, and Vm sin omega t. So to better understand, let me go to the waveform, okay, to find out the average output voltage. In this waveform, see carefully the average output voltage. So the duration to calculate the average output voltage, first we should find out the duration. The duration is, this peak is actually confined, the duration that is alpha to pi plus alpha, okay, and in a complete cycle, that is I am talking about 0 to 2 pi, the number of peaks in any direction or the forward direction, that is 2, okay. That means number of peaks equal to 2, complete cycle 2 pi, and any one peak that is confined between alpha to pi plus alpha. In this way, we can write the expression that is 2 by 2 pi integration of alpha to pi plus alpha Vm sin omega t d omega t. And after simplification, we will get the result of the average output voltage of the load that should be equal to Vm by pi integration of pi plus pi alpha to pi plus alpha sine omega t dt. Okay, that means we can simplify further in this way, that is VDC that should be equal to Vm by pi and integration of sine theta or sine omega t, that will give us minus cos omega t, and consider limit that is that is alpha to pi plus alpha. So after modification we will get that is Vm by pi minus cos omega t, that is cos alpha minus cos pi plus alpha, that will give us that is alpha, that is cos alpha plus cos alpha, or that is 2 cos alpha. So we can modify the expression that is Vm by 2 cos alpha plus cos alpha, that will give us that is 2 Vm by pi cos alpha. So this is the final expression for the average output voltage from the load, that is 2 Vm by pi cos alpha. But in case of half-wave rectifier in RL operation, we have found the average output voltage was that is Vm by pi cos alpha. In this case, we have found the average output voltage is just double with respect to previous one, or half-wave rectifier. That is why this is a actual benefit for using the full wave rectifier circuit rather than half wave rectifier circuit, as we are getting the double average output voltage. Okay, as well as we can define the current also, that is the average DC current, average current, that is termed by IDC, that should be equal to VDC by R. That means 2 Vm cos alpha by pi R, which is taken from this expression. So this is all about for the average output voltage and average output current. Now we should calculate the RMS value also. So we know RMS means it a root mean square. Okay, that means RMS value of output voltage or load voltage, that can be termed by VRMS, that should be equal to 2 by 2 pi. Just the equation can be formed just similar to average output voltage, number of peaks by total cycle, integration of confined region, instantaneous voltage expression d omega t. That is why, as it is a RMS value calculation, that is why we have taken the root mean square. That is why VRMS should be equal to, that is 2 by 2 pi integration of alpha to pi plus alpha Vm square sine omega t d omega t. Okay, so this is the expression for the VRMS. So we can simplify the expression through this way. First, that is 1 by pi Vm square by 2 integration of alpha to pi plus alpha, and we have taken the part that is divided by 2, which is multiplied by 2 in the expression of sine square omega t. That is why we can change this expression to sine square omega t, that means 1 minus cos 2 omega t. So we can have the expression that is Vm square by 2 pi integration of alpha to pi plus alpha 1 minus cos 2 omega t d omega t under root. Okay, now we can integrate the both term 1 and cos 2 omega t. 1 means after integrating we can have that is omega t, and cos omega t, that is 1 by 2 sine omega t. Okay, so we can rewrite the expression in this way, that is Vm square by 2 pi omega t, lower limit alpha and upper limit pi plus alpha, and 1 by 2 sine 2 omega t alpha to pi plus alpha under root. So after simplification, again we can have the expression that is Vm square by 2 pi, considering the limit, that is upper limit minus lower limit, that means pi plus alpha minus 1 by 2 sine 2 pi plus 2 alpha minus sine 2 alpha. Okay, so after simplification we can have that is Vm square by 2 pi minus 1 by 2 sine 2 alpha minus 2 pi under root. So after calculating, we can rewrite the expression in this way, that is Vm square by 2 pi into pi under root. So that means pi and pi both can be cancelled by each other. So the result is, that is Vm by root 2, which will give us the actual result, that is Vs. Actually Vm by root 2, that is RMS value. So the value is Vs. Okay, so this is well defined throughout this expression. So in this way we can calculate the average output voltage as well as the RMS output voltage. So what will be the RMS current? So average RMS, so the RMS current of the output current, that can be defined by IRMS, that is equal to V RMS by root 2R, that is why Vs by R. So this is the RMS, this is the RMS current expression. Okay, so this is all about for the RMS and average value. Now the main important part, due to presence of inductor, we are going to express the all scenario to the proper expression during steady state operation as well as during transient operation. Okay, now the voltage equation from the circuit we can derive by Vm sin omega t equal to R into I0 plus L into I0 by dt. That means the output current I0 can be expressed as I0t equal to Vm by Z sin omega t minus alpha. Okay, this one, and plus A into e to the power minus R by Lt is a complete solution that is discussed in my previous section so many times. So now we are going to find out the value of this constant A by considering the boundary condition, and that should be taken from the waveform. Okay, so to find out the value of A, let we assume omega t equal to alpha. Okay, if omega t equal to alpha, then we should find out the value of I0. So at omega t equal to alpha or t equal to alpha by omega, then I0 equal to what? Okay, so at the point omega t equal to alpha, then I0, that should be equal to capital I0. Okay, and next, if omega t equal to pi plus alpha, then again the value is I0. So keep it in your mind, these two both values. Okay, so we can write the expression to satisfy the boundary condition at omega t equal to alpha. Then the output voltage expression that can be defined by, that is I0 equal to Vm by Z sin alpha minus phi plus A into e to the power minus R alpha by L omega. Okay, that is from the first expression. Okay, again at omega t equal to pi plus alpha, just I have found before, we have found before, again the expression of the current, that is I0, that should be equal to capital I0 at t equal to pi plus alpha by omega. That means for the both case, the I0t, that is same, that is capital I0. So we can express the expression I0 equal to Vm by Z sin alpha plus pi plus alpha minus phi plus A into e to the power minus R pi plus alpha by L omega from the equation, same equation 1. So ultimately after simplification we can have Vm by Z sin pi plus alpha minus phi plus e to the power plus A into e to the power minus R pi plus alpha by omega t, and after simplification further we can rewrite the expression, that is minus Vm by Z sin alpha minus phi plus A into e to the power minus R into pi plus alpha by L omega. Okay, so from the above equations we can say, so we can get or we can write the above two equations, that is satisfying the value of I0, that will be same. Okay, actually both the equation that is expressed by I0, this is I0 and this is I0, so we can correlate the equation. That means this one that should be equal to this one, just I have done here. Okay, that means we can write the expression that is Vm by Z sine alpha minus phi plus A into e to the power minus R alpha by L omega, that should be equal to minus Vm by Z sine alpha minus phi plus A into e to the power minus R alpha plus pi plus alpha by L omega. After simplification, okay, this one A into e to the power minus R into pi plus alpha by L omega minus e to the power minus R alpha by L omega, that should be equal to 2Vm by Z sine alpha minus phi. So ultimately we can find out the expression of this particular integral constant A. Okay, and that is defined by 2Vm by Z sine alpha minus phi divided by e to the power minus R into pi plus alpha by L omega minus e to the power R alpha by L omega. Okay, so we can have the value of this one. That can be taken from the next equation, that is by put the value of this particular A term, just we have discussed previously. So and by satisfying the equation 1, so we can have the actual expression, that is I0t equal to Vm by Z sine omega t minus alpha plus 2Vm by Z into sine omega alpha minus phi divided by this A term, that is e to the power minus R pi plus alpha by L omega minus e to the power minus E alpha by L omega into e to the power minus R by L t. So from this expression, we have taken the common term from this expression. That is why under bracket we have get this term. Okay, that is why again we can simplify the equation, that is Vm by Z sine omega t minus alpha plus 2 pi by Z into sine alpha sine phi minus alpha minus e to the power minus 1 minus e to the power minus R pi by L omega. That is actually we have taken this minus e into minus R alpha by L omega term, that is common part, and we have we are going to express the total thing in a particular exp term. That is why just we have this part I have taken with a positive part here. So ultimately from these two parts we can write the expression exp into minus R by L omega t minus alpha. Okay, this is the actually term which is taken out from this one. So ultimately we can rewrite the expression, that is Vm by Z sine omega t minus alpha plus 2Vm by Z sine alpha that is phi minus alpha, and the denominator part is 1 minus e to the power minus R pi by L omega and exp minus R by L omega into omega t minus alpha. So this is a final expression through which we can define the transient current during RL operation in case of the full wave rectifier. This is the final expression for the total solution of the current. Okay. Now the question is freewheeling diode. As we all know that due to presence of RL load, normally the input power factor is lagging, as well as the all over efficiency or the average output voltage should be decreased. As the negative peaks is there during presence of RL load, I am talking about a particular duration where the inductor starts discharging, and the duration is pi to beta, or in this case that is pi to alpha, whatever. That means when the negative peaks is there, that means average voltage should be reduced in magnitude. As well as in case of the fourth quadrant operation during discharging of the inductor, then the inductive current, that is feedback to the supply, means the current starts flowing from load to supply. That means as the inductive current nature is lagging power factor, that is why input power factor will be affected, and it will be more lagged due to presence of inductive current. So in the both cases, the all over efficiency of the system or of the rectifier, that should be reduced in nature. That can be overcome by using freewheeling diode, and which is depicted in this figure. Okay, this is a schematic circuit diagram in which we are using the RL load as well as the freewheeling diode. That means by using this freewheeling diode, the negative peak that is appeared due to presence of the discharging path of the inductor, that should be not feedback to the supply. That will be free wheels due to presence of the freewheeling diode across the load. That is why no question of this negative peak. Okay, that is why we can replace the total discussion by this waveform also. So these two first waveform, that is V0 and V0, this is for without freewheeling diode and this is for with freewheeling diode, and this is the current waveform, that is without freewheeling diode and with freewheeling diode. So if we are using without freewheeling diode the RL application, that means there the question for the negative peak, just I discussed before, is a negative peak. Due to presence of this negative peak, all over average voltage would be reduced, as well as the input current would be lagging power factor. So as well as when we are using with RL load with freewheeling diode, there is a no question for this negative peak, as the discharging current or discharging energy of the inductor, that should be freewheeled by using this freewheeling diode FD. That is why no question for arising of this negative peak. That is why this is 0. That means average output voltage will be improved. Okay. So this is the major application due to presence of this freewheeling diode. One more thing, similarly it can affect on the output current also. In case of without freewheeling diode, the output current was this one. There is a small means nature of ups and downs, that is ups and down, due to the charging and discharging path. But if we are using the freewheeling diode, then there is a no question for, as there is a no question for the negative peak of the output voltage, that is why it will give us the almost DC. Is a good example for using freewheeling diode. Okay, so thank you very much for your attention and investing your valuable time. So ultimately we have discussed all about for the single phase full wave rectifier with RL load, as well as single phase full wave rectifier with RL load and freewheeling diode. Okay, then thank you.